exoplanets and life beyond the Earth, following by an up-to-date astronomical press release. Before starting, just a piece of information and also an announcement. You may already know, but it's worth to tell that we have planned our live streaming program every first Thursday of month, 7 p.m. Central European Time. You have asked us how it's possible to be informed of the events. That's pretty straightforward. You can follow us on Facebook or Instagram page with the name AoT Koeln. And we also keep posting the advertisement of the event on the Facebook page of University of Cologne. And good news is that we have already set up our next event, and we are happy to inform you that on 3rd of September at 7 p.m. we are hosting Professor Kramer from University of Bonn with an interesting talk about pulsars. Okay, make sure you are comfortable and you have your drink, lean back and enjoy. Without further delay, let's welcome our today's speaker. And after a short introduction about what she is doing, jump into the first part of today's event. Welcome, Sabine, and thanks for accepting our invitation.
Thanks for having me.
Okay, I will give a short introduction about what you are doing, and then you can start. Sabine is a third-year PhD candidate in astrophysics here in University of Cologne. She did also her bachelor and master studies in physics in Cologne. Her PhD research is dedicated to simulation of planet formation. However, as a side project, she is involved in testing calibration unit of METIS instrument. METIS is going to be an imager and a spectrograph on the Nobel infrared telescope. ELT stands for Extremely Large Telescope in Chile, and it is going to get the first light in 2025. It's also worth to mention that Sabine is interested in involving school students in a small experimental physics project to give them a taste of physicist real life. Therefore, she is moderating a program called Schnupper Praktikum to host neighboring school students in a one-day program in the university. If you are interested in that, you can find more information on the address in the comments below this video. Good. I believe that life beyond the Earth is of the most absorbing topics in the astronomy, Sabine. We are looking forward to your talk. Please take over and go ahead.
Thank you. I need to share my screen.
Yes.
So I hope everyone can see it.
You are good. Yeah.
Perfect. Thank you very much, Roya, for this very nice introduction. And I'm very happy to talk about exoplanets and the search for extraterrestrial life. An exoplanet, which is an extrasolar planet, which means the planet is outside of the solar system and it circles around another star. Since the beginning of human cultures, people wonder about other worlds. In this talk, we learn about the different exoplanets discovered since 1995. And the first exoplanet was around a sun-like star, was Pegasi 51 Pegasi b. the star is 40 light years away, and the planet has an evolution. It circles around this, its main star in 4.2 days, which are 100 hours. And the planet which was discovered is roughly half the size of Jupiter. So it is totally different than the planets we know in our solar systems. We will talk about that later on. So most of you have probably seen planets, pictures of exoplanets. Most of them, like my first slide, are artist impression, how the artist thinks exoplanet will look like. But I can only show you very few pictures of exoplanets, which are done by telescopes, because they are so rare. These two were one of the first made in 2008. Now we look at this system a little closer. On the right system, here we see the planet Formalhaut B. This is a little zoom on the planet, which is in here. The planet circles around the star in about 6 times of the distance of Pluto and the Sun. So it is quite far away. It's 113 astronomical units, which means, and 1 astronomical unit is the distance Earth-Sun. So it is quite far away, and the planet has roughly 3 Jupiter masses. And here we see the pictures of Hubble. It's the space telescope, and it was following the movement of the planet over several years. But we don't know exactly how long it takes to go one time around the Sun. But we can guess it has to be at least several hundred years. It was the direct. It was one of the most famous pictures during that time, and it was published 2008. The star Formalhaut is at a distance of 25 light years, and it has roughly double the mass of the Sun. And now we want to look at this picture a little bit more closely. It is in the middle. You have to make the star a little bit, to cover the star, so that we can actually picture the dust and the planets around that star, because the dust and the planet don't emit light, they just reflect light. And otherwise, if we don't shade the star, the light would be the star would just we couldn't see anything of the planet. That's why we have to cover the central star to see the planets. The same method was also used for the left picture. This here we see the star HR 8799, and it was observed 2008 with the Gemini North Observatory and the Keck Observatory. And they actually were able to observe a whole planetary system. And this planetary system is roughly 130 light years away from us. And thanks to adaptive optics, it was possible to show the 4 planets. Yeah, the star is 1.5 times the mass of the Sun. And it was also published, yes. And it's an infrared image. And here in the middle, you also see that the star is covered. like you have seen, there are different, the exoplanets which were discovered or pictured are quite different to this system we know. So, but nevertheless, what we do, what the scientists did was to project what we know about our solar system onto the exoplanets they found. The system is not internationally binding, but it is mostly used. So for example, we have two types of planets: the terrestrial planets. These are rocky planets like the Earth, Mars, Mercury, and Venus, and the Jovanian planets. They are gaseous planets, big planets like Neptune, Saturn, Jupiter, and Uranus. And but because of the different things we found, because the location, not only the size and the mass is important, but also the location in respect to the sun is very important. That's why there is a further classification that you also say where it's located. That's why, for example, you call them a hot Jupiter, because it's a Jupiter-sized planet, but it is close to the star. But it would be a hot Jupiter. This would be like the name for the planet which was discovered in 1995. And for example, the planet Fomalhaut B would be called a cold Jupiter because it's far away. So here we can see that a little bit more detail. Here we see the Terrans group and then the giant group, and here we see the different zones: hot zone, habitable zone, and cold zone. And here is the Earth located. It's Earth's, because it's so every planet which would be roughly the size of Earth would be located here, and also within the distance which is warm would be here. But we also see that there are a lot of hot and big planets very close to the star, which is not visible in our solar system. As we know, the bigger planets are outside. We will talk about that later too. And also you see there are some bigger cold planets further outside found, but there are only very few small Mercury-sized planets found. This has something to do with the observational bias we have. We will talk about how we find exoplanets, and that will explain the gap of observation. Unlike the USS Enterprise from Star Trek, we cannot fly to the exoplanet and scan the planet and figure out what the atmosphere looks like, the size, and if there's life. Yeah, we don't have it that easy. We have only this view. We can look in our night sky and we see the Milky Way and the stars close to our area. That's why we can use the maybe most obvious method. It's the direct method, but it's also the most difficult method, because you need very good instruments which are able to see those exoplanets. As the planets are just reflecting the light and don't shine by themselves, so it is a very difficult task, and we will talk about a telescope which we can do that later. It's, for example, the ELT we already heard of. The indirect methods are much more successful because you can detect exoplanets with much smaller telescopes. When I was in 12th grade, for one of the school works I was doing, I was observing an exoplanet by myself with this only 30 centimeter telescope at the Max Planck Institute in Heidelberg, for astronomy in Heidelberg. And this is the reason why indirect methods, yeah, you can also observe, what I observed was a hot Jupiter, because it's much easier, because the indirect methods use the fact of, for example, the one which several methods use the fact that planets have a bigger mass or are just bigger, and the probability of passing through is higher, and then they interfere with the mass, they interfere with the planet, with a star, and they wobble or other things. So we look a little bit closer to the method, because, for example, with microlensing, the mass of the planet influences the light curve, which is coming from the star behind. The bad thing about this method is you can only do it once, because it's a random event. It's like a planetary system with the planet just passes a star in the background, and by chance it was detected. But there are also other methods like astrometry. They use this method which I told you about, the mass interference, like the mass of the planet and the star are interacting with each other, so the star starts to wobble. So we look at the system from the top, so we see actually the movement of the star. But we can also use the same effect for the radial velocity. So we look from the side on the system, and the star and the planet moves like this. And here we see that the light is shifted from red to blue. And there is another method where it's also good to have a big planet, is the transit method. The planet passes in front of the sun, and the light is blocked by the planet, and this makes a dip in the curve. And we will take now a look at the transit mode method a little more. For example, we know this method from our own solar system. If Venus or Mercury is passing in front of the sun, we can see it actually. The smaller, the harder it is to detect it, because the dip becomes much smaller. We can see, for example, if an alien observer of our sun would look at our system, and then the Earth would only make a dip of the lightness of the sun just by 0.01%, and the Jupiter would already make a dip of 1%. It's a quite easy calculation. You just look at the different. Here I showed you the calculation. It's quite easy. You just have to put the radii squared into in respect to each other. And but to do that, but we don't want to find hot Jupiters, because we want to look for life on different planets. So we want to look for Earth-like planets, because we know on Earth life was happening. So we need very good telescopes like the space telescope Kepler, which can observe those dip from very faint telescopes. So, but we need to remember that the more the smaller the planet, the better needs the telescope to be, and that's also true for the probability of happening. It's very difficult. The probability of transiting is higher the closer the planet is, and the further away the planet, the probability of passing through the line of sight, it's smaller. That's why, the more hot Jupiters, more big close planets were detected than the smaller Earth-sized planets at a further distance. But the advantage of such a transit method is that you can also tell something about the atmosphere, because the star rays passes through the atmosphere of the planet, and rays interact with the gas. And with those absorption lines, we can make conclusion about the elements in the atmosphere. And those absorption lines are also very, very small. That's why you need really good telescopes to measure them. And of course, the bigger the planet, the more you can see. And the smaller the planet, the harder it is to analyze the atmosphere. That's why this is something very new, and we will talk about a telescope which will be able to do that soon. Yeah, I already talked about the NASA Kepler mission, and we see that that this mission really detected a majority of the known exoplanets. And now we come to the EELT. It's the European extremely large telescope, and it will, like mentioned before, have the first light in 2025. And there are the goals to reobserve the exoplanets and make direct imaging, and also then analyzing the atmosphere of those planets. And with direct imaging, we have the advantage that we can image the planets which are not too close to the star, but relatively small. So Earth-like. That is the goal. And this instrument will work in the mid-infrared range to detect oxygen and ozone. And there, the University of Cologne participates in developing the instrument METIS, which is on that telescope, and there we will build a small part, the warm calibration unit here. And now we talk about this this bias of observation while looking at the time scale of detection of those different planets. Here we see that in the early phase, so in the early phase, bigger planets have been discovered. And then with Kepler, also through those observational bias, we also see that a lot of big planets very close to the stars have been discovered with Kepler. And now we come a little bit closer to my topic. Already in science fiction, a planet with two suns was known, let's say, the Luke Skywalker's home planet Tatooine. This in Star Wars was circling around two suns in 1977. And the first real exoplanets in a binary system was discovered in 2011. This is not long ago, and it was Kepler 16b. And this was a gas giant similar size of Saturn. And there are two different kinds of exoplanets in binary systems. The one we know from Star Wars, like the planet circling both stars, like the Earth circles the sun, but just around two stars. And we have a second type, it's called satellite, S-type. The planet circles just one star and the binary circle each other. Yeah, so there are different systems, and now it's really interesting how they are stable, how do the planet form there, and how do they reach the position. And yeah, it's a up-to-date science, as the first planet was discovered 2011. So there is a lot of science going on and a lot of things happening right now. My work is I simulate the system Kepler-38. It's also a binary system. It is very tight, those stars. It's only 0.4 AU, like separation between the binary stars and the semi-major axis of the planet. It's 0.5 AU. So it's roughly half the size of Earth's sun distance. But it's a giant planet. It's a Neptune-sized planet. So we don't. There are two different scenarios of how those planets could form. One of them is that it formed further outside, like the big gaseous planets we have in our solar system, but migrated inwards. And this is we need to understand better, and we do simulations and to know this the process, to get to know the physical process behind it. Because we cannot observe that process because of the time scales we have. We only have the one lifetime to observe, and these planets, it takes much more time to form a star and the planets and stuff. So that's why we need to do simulations. Yeah, so here in the simulation, the planet starts further outside and then migrates inwards. And but how Yoda would say, a lot to learn you still have. So there is a lot of things we all need to learn, and there are new discoveries yeah, every day. So it's quite cool. So now we continue for the search for life. We want to know if there is extraterrestrial life outside, which we can see, and we will also talk about what is needed for life to be, and yeah, and how could that life look like? And here we found it already. This is like an artist impression of a binary system, and with aliens or visitors on it, or maybe we find a green guy. Now we take a closer look on what is necessary for life. First, we need, most famous is, for example, the word habitable zone. I think everyone heard, which read about extraterrestrial life, heard about the habitable zone. This is just a phrase for that the planet could have liquid water because of the distance around the star. Every star has a different distance where this zone is possible. Here we see, for example, a sun-like star. The habitable zone is further out, and a smaller star has a habitable zone closer in. And there are different aspects which are important. For example, that the lifetime of the star needs to be long enough for life to develop. So a big giant star which burns all the fuels within like 10 million years, it's not a good candidate for life, because the area, the lifetimes are just too small. That's why we want to look to Earth-like stars, sun-like stars, or smaller stars, because the sun has a lifetime of 10 billion years, and Earth is already 4.5 billion years old. So it needs some time for life to develop. Now someone would guess, oh yeah, then let's search for smaller stars than the sun. Then the star lives longer than the sun, and the life has much more the chance to develop, to see something. But there is a catch. For example, with Gliese 581, it is 20 light years distance, and it has a planet D, which was suspected to be in the habitable zone. And it's a super Earth, so it's a slightly heavier than the Earth. But there is a problem. It's called connected rotation, and we know this connected rotation from the Moon. The Moon is circling the Earth, and it's always showing us the same side. So we only see one side of the Moon. And this connected rotation leads to, if the planet rotates around a star, that one side of the planet, it's really, really hot. And the other side of the planet, it's cold. So if that planet has an atmosphere, that would suggest that there would be strong winds to even out the temperature differential. So this is not a good place for life to develop, because the atmosphere is very turbulent and with strong winds. So that's why most of the surveys now go back to search for sun-like stars and planets around them. But there are further factors for life. For example, the stability of the rotation. For example, we have the Moon, so our planet rotates stable around itself. We don't have a planet wobbling around, and this really leads to a stable climate, which is needed for life to develop. Also, we need a cosmic cleaner like the Jupiter. We have a big giant planet in our solar system which attracts all those comets or asteroids which come into our solar system and then diverts them or make them crash into it, so we don't get hit by meteoroids too often. And another factor is the magnetic field. This protects us from the cosmic rays, which really can destroy the cells, and also from the solar rays when there's a solar storm. So this is very important. And also, which is very important, is that we are in a relatively calm area, which means there is no young star which is going to explode in a supernova soon and burst away our atmosphere or emits very unhealthy rays. So this is a good spot that we are like in a calm and rather boring neighborhood in our galaxy. Yeah, these are just some of the important factors which are needed for life to develop. And like you see, there are a lot of factors, so it's quite difficult, to find life, because if you look for a moon in a different, you first have a star which is far away and you're so happy that you can detect the star or see it with direct imaging, but a moon around this exoplanet is a lot smaller and also just reflecting. So this really will need top-notch cutting-edge technology in telescopes, and this will there will be a lot of things happening in the next few years and decades. So a huge area. That's why also the Nobel Prize was given to physicists who discovered the first exoplanets in 2019 to open up that interesting field of exploration of exoplanets. So, but also since the beginning of human culture, people were thinking about other worlds or other lives. So, for example, the philosopher Metrodorus from Chios in the 4th century before Christ, he was asking, could there be other worlds, for example? Or Immanuel Kant, from 724, he lived to 1804, and he has written a very famous book, Allgemeine Naturgeschichte, and there he states the assumption that all stars are suns which could inherit worlds. So I give you, for everyone who speaks German too, who want to read the original passage, here is the original passage. Yeah, and there is this one formula which is often cited when there is a discussion about exoplanets. And let's say this has to be, this equation is not 100% scientific. It's more like something where you can think about the factors which are needed to that life is possible, intelligent life is possible. And I think it's a nice thing to think about, but it's not scientific. So, for example, he was thinking about the average star formation per year in our galaxy. You have to take in account, and then the share of the stars with planetary system, and then the average number of planets per stars with in the habitable zone. And if you have a habitable planet, these planets, not all of them have life. And then not all of those planets have intelligence life. So there's also a fraction of that. And from those fraction of intelligence life, the life also needs to have interest in interstellar communication, that we can know about it. And then we also have to take into account the lifetime of a technically developed civilization in years. And then there are different answers to this scientific, this not so very scientific equation. Some people say, like, for example, in the Star Trek universe, they would say 150,000 intelligence life forms. The equation would be 150,000. Yeah, and other people say it's just one, and hopefully it's us. And yeah, so this is a very it's a nice thing to think about, but yeah, also it's very unlikely for us to communicate to another intelligent life form just because of the way the distances we have. Because if something is 40 light years away, a planet, then the signal needs 40 years to travel and 40 years back, which is 80 years. Okay, this could be possible, but the conversation would be very rare. But it's more likely that the planet which inherits life would be much further away, maybe in a different galaxy, which we cannot even detect with our technology today. So, and the next galaxy is Andromeda with, I don't know, a lot more light years. So it's impossible to communicate nowadays. Maybe we don't know what's happening. So I hope I inspired you a little bit to think about it, and yeah, and I hope you're also excited about the new science which come up, the new discoveries which pop up, and yeah, and take a look into that. Thank you very much, and also thank you for hosting me today. So yeah.
Yeah, thank you very much. It was really fascinating. Actually, I was also thinking about the last equation, non-scientific equation that you shared with us. I was thinking that, you know, all these requirements of the life that these days we astronomers name is based on our experience about the life on Earth. And
Yes.
it can be also other things that we are not aware of. And I was in this kind of thinking, and then I found myself in the middle of nowhere. So I thought, okay, it's better to stick to the criteria that we already know. So I have questions, but let's tell our audiences that you can also keep posting your questions under the um, video. Okay, I have already some questions. Let me start with the questions of our audiences, and then later I can continue with mine. What is the likelihood of TESS finding planets that contain organic life?
Yeah, this is a hard question to answer, because this would means I have let's say Fähigkeiten, the word in English. I have knowledge of things which are not yet discovered in science. So this would be a wild guess. And but I, personally, I think it's much more likely to find, for example, microbic life or traces of small life somewhere. Maybe we see traces in the atmosphere which concludes that there could be life on that planet, but 100% sure you can only be if you go there and take a probe and analyze it, but this won't be possible.
Yeah, that's right. I myself know of recent studies that that except water, organic molecules can be also an important criteria for having life. Interestingly, astronomers could find those complex organic molecules which help them to predict a path toward finding RNA. I would say it would be a very special moment when they really can find RNA, even though they are looking in the young stellar objects. But yeah, we don't know exactly. It's hard to find them in this space.
Yes, I think the next few years with new telescopes which are coming up, there are a lot of telescopes, also which ones I didn't mention, the James Webb and all other kinds of telescope, also the ELT in 2025. So with those telescopes having first light, I think there will be a lot of things happening. The same when was happening when Kepler was doing first light. I mean, this period from 2009 till 2018. I mean, they regularly were popping up from NASA news like second Earth found, or so there will be a lot of news coming as soon as those instruments have first light. Yes.
Yeah, that's right. Okay, the next question is that do exoplanets have liquid water on them?
Yeah, this depends on the location of that planet, which circles that star. So we to measure the atmosphere where we can detect traces of water is nowadays really difficult. So they are. But we can guess about it. So we know in our solar system, we know how the sun works, we know how the physics behind different stars work, and so we can calculate the area in which the rays should be still powerful enough to have a planet be warm enough with an atmosphere to keep water liquid. And so that's why we can say those planets could have liquid water in that area.
Okay.
But yes.
But is it the case that all exoplanets have these? I think the answer is no.
No, I mean, what is when we look in our solar system, for example, Mars, a lot of scientists think there was liquid water on Mars, and also the range where it is still like on the edge of the habitable zone, depending on what you take into account, which parameters it's inside, sometimes it's outside. So some scientists believe that there was water. That's why there are so many missions now. I mean, you heard probably a few missions are going to start it already this year, or are going to start this year. Yeah. And they are all looking for traces of water or life. And yeah, so as in our solar system, there are planets which is no water, or we really have to search really, really hard for it. This is also possible for planets outside of our solar system.
That's right. Okay, the next question is that are the rising number of satellite constellation an issue for Earth-based observations? It's not clear to me. Are the rising number of satellite constellation? If anybody in the committee could guess what our audiences mean with this question. Okay, we can go to the next question. How much can we tell about the composition of exoplanet atmospheres?
At the last word, please.
How much can we tell about the composition of exoplanet atmospheres?
Atmospheres. Mm-hmm. Yeah, this is a very new topic, and it's just started. So I remember there was an article. I don't have it right now with me, but there was something beginning of this year or something that they found traces of water in an exoplanet's atmosphere. So they are already analyzing those atmospheres, but yeah, this would require a small research of me to find out more information.
Okay, so we are looking forward to that.
Yeah. Oops. Yeah.
Do you have us? Do you hear me?
Yeah.
Okay. And the next question. Okay, great. Our audiences are keep posting questions. That's very good. Why does Jupiter not migrate inwards, or did Jupiter migrate inward some time ago?
Okay, I'm not that into the topic of the physics of solar systems, but the migration process happening in very, very early stages of the development of a star. So in this time where the disk, the protoplanetary disk, is full of gas and dust, and with that there are different physics comes to play, which, for example, has to do. You can look at it as we simulate it as a fluid. We look at this like this, and then there you can see that there are forces which are pulling the planet because of the Keplerian rotation, which are pulling the planet inwards, and there are other forces because of this fluid-like the gas. It behaves like fluid, and that's why we get a pull outwards and we get a pull inwards, and the net, depending on the strength of those forces, is either migrating inwards or outwards. And this happened in we think it's a scenario that this happened in those systems which have planets very close to the stars.
Okay.
Because we think that we know that the planets cannot develop there because of the heat and the winds. You need the colder areas in the protoplanet stellar disk.
Maybe some question that is very close to what you already explained is that do we have another planetary system that astronomers have studied that closely, or our information is only coming from our solar system in reality, and the other information we have are based on simulations?
Yeah, this is, I think, before the first exoplanet was discovered, also we thought we know how planet formation works because we studied our solar systems for several decades and we found new things, but still we thought we understand the processes behind it. And then the exoplanets were discovered and they look totally different. So we needed to adapt our theory of how solar systems develop. And so we know a lot from our solar system. But as we have new insights or new information, we have to expand that theory, and this is possible through observations of different stages of exoplanet development. For example, we look in the infrared, we can look at early stage. In the visible, we can look at a more developed stage where the gas and dust are already gone and stuff. So this is very important. The observation is very important, but not only the observation, we also need to see how those different stages fit together, and that's where simulations come to play, to see how to connect those different stages and how physics
very
work.
nice. Yeah, that's right. Okay. Do we have any idea what we would do if we ever found extraterrestrial life? I think that's a question that philosophers should answer.
Yeah, I think when the Voyagers were sent out, the people were thinking about it, how to communicate with the aliens. I mean, they made those symbols on the spaceships in case aliens will find it. So I think there are some people who thought about it, and a lot of movies makers have thought about it, and so I don't know.
Maybe it would be nice if our audiences write their answer below this video, right? To see how people are thinking about that. Okay, the other question is that do orbital resonances affect habitability?
Yeah. It depends. I think as a stability and the distance to the stars are very crucial. I think they influence. So life can only develop if a planet has a stable orbit. And
Okay. So far we had a lot of questions from audiences. Let me ask my own questions. You can still posting your questions, but meanwhile I'm going to ask mine. The first question I had was that you nicely explained what exoplanets are. Okay, they are planets orbiting around the stars except our sun. And you also mentioned that in 2011 they could find a binary system, right?
Yes.
It was my question that if they could find any planet around a multiple system, like not a cluster, but 3 or 4 stars, which shows a planetary system around.
Yeah.
Maybe not.
This is probably also something about definition, how you define what is a binary system, what is a multiple system, because the distances between those stars can be really far and still be connected gravitationally, but not just loosely. So, for example, if a binary system, a tight binary system, could also be somehow in connection with a third star, but the third star is so far out that it's not influenced. But of course, the chances for a stable orbit, the more forces are acting on that planet, it gets difficulter and difficulter to keep a stable orbit and not be ejected or pulled onto the star. So the chances are much higher the less stars are involved, and it gets more complicated with more stars. But also, if the stars are really distant, then per definition it could be a multiple star, but they are far away.
Mm-hmm. Then the other thing that comes to my mind while you were presenting different methods to detect the exoplanets, I was thinking, how do astronomers know which kind of planetary system are facing with to select the best method to detect that exoplanet?
Yeah, I think it's just surveys. They look like Kepler. They look at so many stars and measure them. Look with one method because Kepler can only measure the transit method, and they just it's chances. Like it's if you measure a lot of stars, you have a higher probability of finding exoplanets, and this is how you do it. You cannot look at a star and say this star it has an exoplanet, and I will just measure this star and find the exoplanet. You can do that if you know that star has an exoplanet and revisit and reobserve that with another telescope and to proof to revisit and see that it's really an exoplanet, that the signal is regularly and stuff. This you can do with one telescope and choosing one star. But to really find and hunt exoplanets, you need surveys. That means they just want to go and track the whole sky and find them.
Okay, very nice explanation. And another thing that is kind of comment, not question, it was very interesting for me that one of the criteria for finding life is to have, let's say, cosmic cleaners. I think you phrase it as this. It was very interesting while it seems that our solar system as a whole made Earth a habitable planet, right?
Yes, there are so many factors, tiny things which influences that we are here today and talk about this topic. These are just a few major factors, but of course there are 1,000 other smaller things come to play when during the course of life to develop. Yeah.
Yeah. I have 2 more questions from the audience. Is the inclination of the Earth's axis also decisive for its habitability?
You mean
I
probably
think,
that
yeah, I think,
yeah. Yeah, I think this, of course, it's stable like it is today, and also the mild climates are also It depends. If you look at life, I mean, there is life which is happening at volcanic areas or wherever we think there is. It's so microbic life can happen a lot of places. So hot would be probably enough, but we know for us, for the other life forms which are more complex than microbes, it is nice to have a climate which is not too hot, not too cold. And so I think it really helped the different climates we have on Earth to develop this variety of life. Yes.
Yeah.
But this is something, this is not my research topic. So this are just...
Yeah, that's right. A bit far from this, and one, let's say, kind of technical question is that how small can a telescope be to discover an exoplanet?
This really depends on the system you are looking at. To discover, it's always good to have a big telescope in space to observe a lot of telescope automatically. But if you want to revisit one, like the one, maybe an exoplanet which is close to the Earth, which has a big planet like a hot Jupiter circling, you can go down, like I discovered it with a 30 centimeter telescope. I think maybe you can go a little bit smaller, but I mean, you need a telescope which is very stable. You need to have accurate, you have to follow it over like 4 or 5 hours accurate. So you need a good CCD chip, like a camera on top. So I don't think it's possible just with your binoculars or like a little telescope, like 10 centimeters, and put your normal camera behind. Like you need a cooled camera for that. And so, and I don't know, probably those institutions like observatory or something, they don't put those cameras on a smaller telescope than probably 30 or something. So it has to be it makes no sense to put a high detection camera on a small telescope. So that's why I think so 30 should be
Okay.
Yeah.
Good. We get a lot of questions today, and I think maybe we can finish this section of the event. Thank you very much, Sabine. It was very nice to have you in our second event with this inspiring presentation and topic. You can stay with us toward the end, or if you have other things to do, please feel free to leave the meeting. Yeah.
Thank you very much. I'm excited on the other topics coming up.
Okay, great. So then thank you all for accompanying us until now. I hope you have enjoyed so far. And I hand over to Alina for the second half of our event, which is press release. Please, Alina.
Thank you, Roya, and thank you, Sabina. It was a wonderful talk. And so maybe we can move to the new session now. So I can share my screen. And yes, so I hope everybody can see it.
Yes, you are good.
Okay, so the first thing we have to announce is our new logo. You might have noticed. So we are so happy to introduce our new logo, and it was done by one of our friends, Mr. Akhil Jaini. And so thank you so much for Akhil for this wonderful logo. And so this time we are talking about some recent events, and the first one is comet Neowise, and I hope everybody would have tried hard enough to watch it or observe it, and because it appears once in 6,766 years. So it's a once in lifetime opportunity. And if you didn't observe it yet, wait till the end of our presentation. We will tell you there is another chance for you to watch in upcoming days. So coming to the comet Neowise, the people who already followed our quiz competitions during these weeks might have answered already about the tail of a comet. So that was a pretty interesting thing. So in comet Neowise, we have two tails, and one is made up of
Alina, sorry for interrupting you. I think your slide is frozen. We are still on the first slide. At least mine is on the first slide.
Oh, is it moving now?
No.
Or
no, it's not working at the moment.
Oh, I'm so sorry. Oh, can you see it now?
Yeah, there you go.
That's
okay. So I'm so sorry for that. And okay, let's continue. So the first, so I was telling the comet Neowise have two tails, and the first one is made up of electrically neutral materials such as water, ice, and dust particles. And another one is from the plasma, like you see in aurora. And the another pretty much bigger news for this month was Perseverance and the Mars mission sent by NASA. So you all know, you might have watched online also regarding this. And the goal of this mission was seek signs of ancient life and collect rock and soil samples for possible return to Earth. And there is another big news in this, because we had Ingenuity on Mars rover. So Ingenuity is the first robotic helicopter on Mars, and it's actually a helicopter on the Mars rover Perseverance, and it tests the technology to scout interesting targets on Mars, and the plan is to find out the best driving routes for Mars rovers. Every time it fly up like a normal helicopter, and then when it comes down, it's like it communicate with the Mars rover and continue. So it's like it's a 30 days mission. So if it is working well, it would be the first robotic helicopter on Mars, and we can continue explore on a very good time in altitude ranges like 3 to 10 meter above the ground in Mars. And talking about the Mars missions, we have some other Mars missions which went recently. So the first one was Emirates Mars mission called as Hope Probe, and this is the first Arab mission, and it was to provide a complete picture of Martian atmosphere and its layers, and it will help answer key questions about the global Martian surface, atmosphere, and its loss of hydrogen and oxygen gases into space. And another one was Tianwen 1, and it's a Chinese mission. And the interesting fact about the name Tianwen is that it comes from a long poem on the same name written by Qu Yuan. Sorry for the Chinese friends if my pronunciation is not correct. It's one of the greatest poets from ancient China. And this poem contains a series of questions starting like how the universe is created and all. So the meaning of this word, like Tianwen, means heavenly questions. Or like that. So, and the first, the mission of this, or the goal of this mission is to find the evidence for current and past lives and produce Martian surface maps and characterize Martian soil composition and water ice distribution and examine the Martian atmosphere and in particular its ionosphere, among others. And almost these three missions, Hope Probe, Perseverance, and Tianwen 1, will reach Mars by 2021. So, and I think Craig might have some news to
Yeah.
tell
Yeah.
us.
Correct? Yes.
Maybe before you moving to the next news, can I ask these three probes?
Mhm.
Are they going to come back to Earth or not?
Mm.
Do you know?
Oh, I don't know. I only know that like Hope Probe have a 2-year mission, and I'm not so sure whether they are planning to bring it back. But of course, for Perseverance, they are planning to bring it back, the soil and
Yeah, that's
materials from Mars. So of course, and I'm not so sure about
the
others.
other two. Okay,
Yeah.
that was exactly where my questions come from because we need some samples from there, right?
Yeah.
Okay, nice.
All right. Yeah. So I will talk to you about Pluto. So there's some interesting news about Pluto that came up recently from Nature. So you've probably all seen this image of Pluto when New Horizons made its close ascent to Pluto and took these wonderful pictures. But now New Horizons has gone past Pluto and has taken other pictures from the reverse side of Pluto. So scientists are currently looking at these images and seeing uh, some new interesting features that have only been theorized before. So anyways, the side that we see, the nice clear image that you saw at the bottom of this picture here is, the side that's facing the sun. And you can see the Sputnik Planitia, I think it is, this very light spot, which is kind of like the left ventricle, which has all of these glaciers, massive glaciers, that might influence Pluto's atmosphere more than we thought before. Um, so what typically happens is that, or what we think happens, is that when Pluto rotates and then there are sides of the glaciers that get illuminated by the sun, and then it turns some of the ice into vapor, and then this vapor starts to rise and starts to create some of these mountains and these basins that we see. And there's also, a lot of nitrogen that we can see in the atmosphere, and, ice. So yes, um, so this subsurface ocean that we believe might be there, that is rising up and creating these massive glaciers and ice shards, has been thought of before, but this is the first sort of strong evidence that we have for this theory. Uh, so now that New Horizons is kind of on the opposite side and moving away from Pluto, it can't take very clear images. So the clear images that you would see above the white line, that would be maybe 75 meters resolution. And in these blurry images would be more towards 2 kilometers or so. Um, yeah, and so the near side, or the side that we would see, the very nice image that we have from New Horizons, you can see there's a lot of red in some of these mountains, and it's laced with ammonia, and it's Yeah, very critical observation, because this means that there is some organic molecules in the atmosphere that can sublimate and sort of turn into vapor at the base, and then freezes and becomes part of these ice shards or these giant mountains in the glaciers. And so there's some astrobiologists that would say that you need three things to create a habitable planet. Is one is that you need to have a strong source of liquid water, and then you need to have these organic molecules, something that can create life, and then you would need a source of energy. And with these observations from New Horizons, we can see that there is a source of liquid water when sunlight hits the surface, and then the water vapor starts to rise, and then that gives you a source of liquid water. And we can see from the red terrain that there is some ammonia there, some organic molecules. And so now we just really are missing a source of energy, or a stable source of energy, so to speak, because the orbit of Pluto is quite eccentric. So you know it as the most distant object, so to speak, in our solar system. But in its orbit, it can range between, well, at its furthest extent, is about twice of its closest approach to Earth, or to the sun. So there's a lot of changes in the surface temperature. And this has a lot of effects for the history that we know of Pluto.
Does the New Horizon telescope have also a spectrograph, or it's only an imager?
I think it's only an imager.
Okay.
The spectrograph, or the spectroscopic observations would have been done from Earth.
Mm-hmm. And yeah, it's not going to get any sample because it's a telescope, it's not a probe, right?
Right. Yeah, mm-hmm. And it has already passed, and it's on its way out of our solar system.
Mm-hmm. Okay.
But yeah, so looking at the spectral data and looking at all of the molecules that we can see in the Pluto's composition, we can see that there's a lot of methane, ice, and a lot of other things in the ice belt around the equator of Pluto. And then this exists on the plateaus and mountains, but we don't really know how they're formed. But yeah, so this is a very nice observation, and it's continuing to make people interested in Pluto. Pluto's still not a planet or anything like that, but it gives new insight for how or where there might be a habitable zone. And even these very distant objects might be able to have the components necessary to make life. It's just at the wrong distance from the sun. It doesn't really have enough energy. Yeah, and then this is a very nice image here. So, I mean, we've had a nice presentation on exoplanets and things like that, and you've learned a little bit about the methods on how we would detect exoplanets. So transiting events or gravitational lensing, all of these things are very, they're nice, they're definitely existing, but they're not direct images. So what we had recently this month is the first direct image of a multi-planet system. And this is in the Muscat constellation. Mm-hmm. And what you can see here, so this sort of bright nucleus is the sun of TYC, yeah, with this very long name that we give for the star. And then these arrows would indicate the planets. There's two giant planets that are orbiting, and some of the other dots are just distant stars that are showing up in this image. So these planets are very, very massive, more the size of Jupiter or something like this. And they're very far away from the star. So I think like 160 and 320 times the distance of the Earth-Sun. So that's very far away. If you look at our own solar system, Neptune is 30 times the distance of Earth away from the sun. So this is very, very far away. But it's a very nice image because it's the first direct image of a multi-planet system. And taken with VLT, which is the Very Large Telescope, the precursor to the Extremely Large Telescope mentioned today. Yes, and the Sphere instrument on the Very Large Telescope, which is also located in Chile. And so for the star that you see in this picture, they have something that blocks the light from the star. And this is so that we can study the atmosphere, sort of the region immediately around the star, and how we can detect planets like this.
These multiple system is observed with VLT. Maybe you mentioned, but
Yeah.
VLT. Okay.
VLT, Very Large Telescope.
Mm-hmm. Yeah.
It is very large. Well, yeah, 8-meter diameter lens on the telescope.
And then in which wavelengths? Maybe it would be interesting for people to know.
I don't think I got that information.
But it must be infrared.
This is infrared, yes. You wouldn't get an image like this with optical.
Yes.
Yeah.
But yeah, this should be infrared, but I don't know the exact wavelength. Sorry.
No, that's fine. Okay.
Okay. Should be good.
Okay, then we can talk about the observational side of astronomy. So what you can see in sky for this month. So as I promised, I'll talk about nearby and how you can observe the last chance you have. So in the western sky after dusk on Thursday, that means today, the path of fading comet nearby will carry it closely past the globular star cluster M53 and NGC 5053. If you don't know, it's exactly shown in the figure. And if you use like find the trio, a finger's width above or like 1 degree to the celestial northeast of the medium bright star Diadem, also known as Alpha Brancis, and the comet, the star, and the two clusters will appear together within the field of view of a telescope at low magnification in this red circle. So this is your last opportunity to get a picture or like observe nearby. So just go for it. And another one, Craig, do you have something to say about the meteor shower?
Yeah, I can comment on the Perseid meteor shower, which should be coming in the middle of this month, but first half of this month. It's a very nice thing to see. The peak will be on the 11th and to 12th overnight.
I think the good thing about these meteor showers are that people do not need to any special instruments. Only maybe a dark sky would be enough to see them.
You would need a dark sky, so you'd need to get out of the center of Cologne.
Yeah, sure.
Whichever city you're viewing from.
Yeah.
Yeah.
That's
there
right.
should be about 100 meteors in the shower at the peak of the
Yeah.
meteor
Oh.
shower.
Oh, that's nice. And I love August because it always have some meteor shower on the weeks. So it always have high peak of meteor shower.
And
It's a
I think the
good,
weather is
good month.
also good enough to go
Ah.
outside the city and spend one night. Yeah, but with the other meteor showers, I think you cannot spend one night outside, or at least it needs some equipment.
Yeah, that's right. And the other one is the Ganymede shadow and the great red spot across Jupiter, and it will be like in August 14th from 10:30 p.m. ADT. So I hope you will observe this also, and these are the three most important things you can observe this month. And if anybody have any questions for the before we close.
I don't see any at the moment.
Yeah. Okay. So then it's time for us to announce our upcoming event. So our talk series number 3 in the next month will be done by Professor Dr. Michael Kramer, and he will be talking about pulsars, the densest objects in the observable universe. I hope we will meet you on that day. And thank you for joining us today. And that's all it from us.
Yeah, if you have further question about our today event, you can still post your questions our Facebook and Instagram webpage, and we would be responsible for answering them.
Yes. Thank you so
Okay.
much.
Yeah,
Thank you so
thank
much.
you. Have a clear sky.
Yeah.
Okay.
Okay.